I'm soldering some 1-watt LEDs onto their heat sinks. This will accomplish several things. First of all, they'll have a heatsink. Secondly, the rather difficult to see scratch that indicates which one of the two tags is the positive tag will become easier to use because the positive tag markings on the heatsink are much clearer. You seem to be tinned already, which is nice. The third benefit is that I have other tags here for wiring. The 3 positive tags of the heatsink are connected to each other and the 3 negative tags of the heatsink are connected to each other. So let's do the... ooh, that's the positive. First, remember when you're soldering, you have to tin the components first, that is warm up the tag and then apply solder to it. And then when you come to actually join them, you just melt the 2 lumps of solder using my Weller soldering iron that I've had for about 40 years. Now the positive was first, so that goes over here. But we mustn't forget the whole point of this was actually, or a third of the point was a heat sink. So let's put a bit of thermal goo on there. And with a solder tinning on all 4 tags, I now attempt to line them up and solder them together. Now, with all that talking, did I manage to keep them the right way around? Well, here is a 3-volt supply from the bench power supply, and looking away because these are rather pinpoint bright, yeah, that looks as though I got them the right way around. Of course, LED, light emitting diode, one important part of that is the diode. Current will pass in one direction. You can apply a positive voltage here and conventional current will cross to the negative tag and the LED will illuminate. Being a diode, however, if you did it the other way around, if you applied the positive to this side, no current would flow at all. That's what a diode did originally. And then somebody spotted one day that certain diode materials emitted light with great efficiency. And the light emitting diode was born. They emit light with one single colour, so this is actually 3 LEDs to get white, a red and a green and a blue presumably, although I'm not entirely sure. And these are what are called warm white, with a little bit more yellow than the other ones known as cool white. Anyway, why am I doing all of this? Well, I've been asked to make a theatrical makeup mirror. The kind of thing Birdman, for example, that Michael Keaton sits in front with light bulbs all the way around. Now in the UK, and probably most of the rest of the world, incandescent bulbs are becoming illegal and impossible to obtain, and quite expensive as incandescent bulbs if you can get hold of them, and their replacements are very expensive as well, halogen bulbs or LED bulbs. So I thought that if I drill some conical holes, this was using a chamfer router bit, if I drill some conical holes in some wood that I can make a mirror frame out of, and if I put the LED at the bottom of that conical hole, then I've got a very cheap, these are about 49p each without their heat sinks, these LEDs, I've got quite a cheap and quite an efficient mirror. This is going to be very bright in your eyes, so I've got to find some way of attaching a diffuser over here, which I haven't quite figured out yet, but we shall see. Gosh, it's actually the correct size, that's amazing. LEDs have another peculiarity. Even if you're applying the voltage in the correct sense, they exhibit high resistance until a threshold or forward voltage is reached. And in the case of these particular LEDs here, that is 3.2 to 3.6 volts. Once you reach 3.2 to 3.6 volts, current begins to flow and the LED emits light. To cope with the varying resistance of these things, you can't use any old power supply. You need a specialist power supply known as an LED driver. This particular one takes mains input, glances nervously to the floor to make sure it's not plugged in, and outputs, well, it doesn't output 3 volts, it outputs 12 volts. It'd be inconvenient to source each LED individually, so this kind of a driver expects you to power 3 LEDs in series. In fact, they're too bright if I do that. I've done a little experiment. I'm going to power 4 in series, which instead of giving me 300 milliamps per LED, gives me 200 milliamps per LED. There's also the internal resistance of this to figure when you're working out these currents, and the total illumination from about 20 of these things becomes a little bit more acceptable. So we're going to apply this 12 volts across 3, or in my case 4 LEDs in series. You may have seen LED strips, long strips of lots of LEDs, again to be powered by one of these. And what they consist of, if you look at them, you'll see cut points, and the cut points are every 3 LEDs. So the power comes in, is routed in series through 3 of the LEDs, and then in parallel onto the next group of 3, and it's then routed in series through that group of 3. So each group of 3 determines the voltage that each LED receives, or group of 4 in my case, and the total capacity in terms of current of this driver, in this particular case 1.5 amps, determines how many of those sets of 3 LEDs you can have in total. I've been thinking about the order of operations here. This is a trial piece, that's the actual frame material, so those cones will be central. But the wiring is going to run down the back of the holes here and really should be covered up. And then there's also the question of how to hold the mirror glass in place. So I think the answer is to resaw off the back here, 1/3 to 2/3 or 1/4 to 3/4 before I drill the cones, or route the cones. And I think I'll go as far as mitering the corners of the frame and putting some screw holes through in the positions that will hold the back on, take the screws out again, before I resaw the back off. I'm going to use my miter sled on the table saw for making the mitered corners. As you probably know, when you're making a miter sled, you try to get this angle as close to 45, or rather 135 as you can, but more important is to make this angle here exactly 90. And then you have an A side and a B side, and if we have a look at my frame beginnings here, this is the left upright, this is the right upright, that will be a cross piece at the top, and I'll be making the corners A, B, A, B, A, B, A, B. So this one here was cut like that, and I'm about to cut the first cross piece at the top like that. The other consideration is the number of bulbs. It has to be divisible by 4 because that's the number of LEDs that will be in series between the 12 volt rails to give me the level of illumination and current consumption that I want. And I've decided I'll have 5 bulbs on each of the longer uprights, and I'll have 3 bulbs on each of the shorter horizontals. As always, if you have a screw that's threaded all the way up and you're trying to use it to join 2 pieces of wood together, if you make a single pilot hole all the way through, then what the screw can do is actually jack the work pieces apart. So I'm using one of these bits here that drills the pilot hole in the far face piece, but also drills me a counterbore in this rear piece here, and a countersink as well, although I'm not so much interested in the countersink as I am in the counterbore, the wider hole in this piece on the side of the screw head. I probably haven't mentioned this thing for a while. I don't actually have a vertical drill press. Instead, I use this miniature milling machine, which works just as well. I have a rear vise face here, which I've set to my 15mm. You on your drill press will probably have a fence on your table. And I've set the depth stop on the milling machine so that the countersink here just enters the workpiece. You might ask, do I actually need to put the screws in and then take them back out again? Pretty important to take them back out again before performing the resaw. Well, once again, wood screws are not precision made devices, and they do tend to move the pieces apart as they cut their threads. And this might just prevent that happening. I'm going to use my homemade bandsaw, the subject of the last N videos, where N is quite a large number, to saw the back off the frame pieces in about the ratio 2/3 to 1/3, or maybe a bit more generous on the front part than that, maybe a little closer to 3/4 a quarter. And I'm going to reference off the good front face, and in all the reading I've done to improve my bandsaw technique, probably the most important thing I've learnt is go as slowly as you can, and even slower than that if you want a clean cut. Plus have, of course, a sharp blade, and just check that you haven't got any drift. So there you have it. Here's the center channel for the LEDs and, well, that way up actually, the LEDs and the wiring, and the edge channel or rabbit here for the mirror. I've done this first and then I'll put the cone drillings through. I didn't want this to mess up the bottom of the cone holes. There are good reasons why we don't drill holes with router bits and why we don't route with drill bits. And one of the reasons why we don't drill holes with router bits is chatter. If your router bit spinning at very high revs, somewhere between 15,000 and 25,000 RPM, is inside a close-fitting hole, any vibration that starts has, as it were, nowhere to go. And if you happen to hit some kind of resonant frequency, either the bit holder, or the router itself, or the material, then you get a very nasty build-up of vibration, or what's called chatter. Now, I wouldn't be considering this at all, but for this being a chamfer bit rather than a cylindrical bit. It's not really tightly enclosed in a hole until it reaches the shoulder here, and I'm only going to go in about 1 millimeter or 2 onto the shoulder here, and that is indeed, because I've done a couple of experiments, where the chatter begins. And the 2 experiments were to sort out the best speed to use. I had this on about 3/4 of its maximum. I've turned that down a bit. And of course, the bigger diameter your cutter, the more you should turn down the speed anyway. The other piece of good news is that this is one of my really posh tools. This is a Fest tool, and as a plunger router, it is superb. There is no play in the supports here and here. And the other thing I'm doing is I've clamped the workpiece to one of my most massive surfaces, this cast iron extension to the table saw. The more you couple this to a massive surface, the greater the inertia you give it, and hopefully the more you damp down any tendency to start vibrating. Well, that first hole did chatter quite badly, and just here you can see tool marks. So this bigger piece of wood than my test piece of wood will have a different mass, a different resonant frequency, so that's not a huge surprise. And for this second hole here, I actually went back to setting 4 on the router, about 3/4 of its maximum speed, and I've got a nice clean hole here with just a little tiny bit of unpleasant noise at the end. That's all the holes drilled, and now I've got it face down on the table, glued up and clamped with this band clamp. A mitre joint is, to all intents and purposes, end grain to end grain, so it's not all that strong, and the larger the contents of the frame are in comparison with the frame size, the worse it gets. My original intention was to put some splines in. You pop it in a jig like this, and you use your table saw to cut something like a 4 or 5 millimeter section out of here, into which you place the spline. But now I've seen the channels cut out, I realised that it's much easier just to put an L-shaped piece of wood into there. I was going to cut the L-shaped bits of wood out of this little bit of oak here, but I can't easily get the grain direction correct for strength, so instead I'm going to cut it out of this 3 millimeter ply, and I'll cut it on the bias so that I've got grain that way and grain that way. The wiring can look a little confusing. I certainly got lost a couple of times. But if you imagine a more traditional picture of a circuit with a mixture of parallel elements and serial elements, with the power rails at the top and bottom, those rails are feeding in parallel the supply voltage to the 4 strips of 4 LEDs in series. I know there's 3 here, but I decided to use 4. And then you imagine this being stretched out, you get the kind of thing we're doing. So the positive enters here and goes to the top of the first chain of 4 LEDs in series, but these two are bridged together, and it also hops to the start of the next series of 4, and once again hops to the start of the next series of 4, and once again to the last series of 4, and in each series the yellow cable is carrying the current through the 4 LEDs connected in series. And then a similar thing with the ground. The ground is here and is bridged off the other connected negative tab on the heatsink here, again to the end of one of the chains of 4, and again to the end of another chain of 4, and again to the end of the last chain of 4. And there we have it. When I was first imagining wiring this up, I did actually picture the LEDs this way up, but of course the whole thing has to be flipped over so the LEDs poke through the holes here and into the cones that are drilled in the face side. So for the moment I've got these little tubes of masking tape holding it down, otherwise they're sprawling all over the place and you can't follow what you're doing. But I will hot melt glue them into place once they've all been flipped over and they're in their holes. You can't see in here today, which is a fairly nice day, so the room is well lit, that these are very bright. When you're sat in front of it, they burn after images into your eyes quite quickly. So as I mentioned at the outset, I need to think of some kind of diffuser. The first idea I had was to put theatrical gel in front of them. This is the sort of thing that goes in front of big stage lights. Normally they're coloured, but you can get frosted, and that was my first thought. Maybe one, maybe two thicknesses of this, but I would have to cut out some really nice circles, and quite a lot of them, or some not so nice circles, and make some rings, wooden or metal rings, to hide any raggedy edges in my cutting out attempts. But then I had an idea. Ping pong balls. They might work as they are. I need to try this in a realistically lit room. I might have to cut holes out of the undersides if it blocks too much light, but I think that's going to work. And it certainly looks like the real thing. Cutting holes in ping pong balls turned out to be something of a challenge. You certainly don't seem to be able to drill it with any kind of drill I possess, nor can you easily use a knife on it, but the disc sander does a nice job of, well, it kind of melts it, kind of abrades it. And ping pong balls have a seam, or at least these do. I can just about see it, but I do switch the light on behind it to check where the seam is. It also has the added effect of cleaning the disc. And that can be reasonably easily tidied up. And the final, hopefully final, challenge is gluing these ping pong balls on. I can't imagine hot melt glue working. 3M77 glue doesn't work, but surprisingly a gel cyanoacrylate and activator does work. So I've made a little cutout slightly larger than the rim of the hole, and that allows me to put a bead of CA around the edge, and then a drop of activator or kicker, and then trying to keep the hole exactly downwards, because it does throw a shadow if it's not exactly in the middle. We pop the ping pong ball on like that, and seems to work.